Welcome to Data Science with EJD. We're still going on with regression algorithms in supervised learning. And of course, supervised learning is one of the branches of machine learning. Okay, so our learning object here, our focus is on regression trees and forests. So remember, under classification algorithms, we talked about decision trees and random forests, and I also made it clear that we could use decision trees and random forests also in the context of regression, and that is why we have regression trees and forests in this situation. So our learning objective is to understand and implement regression trees and random forests for continuous output prediction and evaluate their performance compared to linear regression using a real world data set. Okay, theoretical foundation. Of course, regression refers to a set of statistical methods used to estimate relationships between a dependent or target variable and one or more independent feature one or more independent feature or variables. In continuous regression, the target variable takes continuous numerical values. When we did classification, the output there was to say, okay, whether something belongs in one group, in one category or the other. But here, the focus is on getting a numerical output that is a real number. All right, so let's talk about regression trees. A regression tree is a decision tree that splits into regions and fits a constant value, typically the mean of the target variable in each region. So under classification algorithms, I used an example of having, you know, like different, okay, I think it was under forest I said that, right? That it is the aggregation of different trees, right? So here it's more like you have a county with different words or something like that, and then you're getting the average value of everything to represent the whole thing, right? So regression tree is a decision tree that splits the data into regions and fits a constant value, typically the mean of the target variable, in each region. So the advantages of regression trees include that they capture a regression tree captures nonlinear relationships. It handles feature interactions automatically, and no scaling of data is required for regression trees. The disadvantage is that it has high variance, it can overfit the training data, and it is less smooth. So it gives less smooth predictions due to piecewise constant output. Okay, and then we go for random forests for regression. Of course, you saw random forest for classification previously. So a random forest is an ensemble of multiple decision trees trained on random subsets of the data and features. So it's more like you have many trees and you're putting them together. Okay. I want to break this down um for easier handling. So I mean, I dealt with working with Jupyter Notebook in under data analysis, first of all, under scientific computing with Python, and I included that in the playlist for data analysis with Python. So that's how you can work with regression with Jupyter Notebook. So the final prediction is the average of the predictions from all trees. So here you're talking about regression trees. Under random forests, you put all the trees, it's more like you get the average of all the trees and put everything together to get your random forest. So the advantages include that it reduces overfitting of single trees. The overfitting, one of the challenges of single trees is overfitting due to high variance, right? But for random forest for regression, we have reduction of overfitting of single trees, and we have the fact that it is robust to noise and outliers, and it captures complex patterns. For disadvantages, because we are dealing with a forest, it's more overwhelming, and so because of that, it is less interpretable and it is computationally intensive. It requires more compute facility, so to speak. So looking at comparison, so we are comparing the we're comparing regression tree and random forests with linear regression. That's like the basic machine learning tool. So, for instance, if you look at the model type, linear regression is parametric and it is linear, and regression tree is non-parametric and it is non-linear, whereas random forest is an ensemble of non-linear models. Then interpretability, you can highly interpret linear regression because it's all about knowing the coefficients and all that, right? And for regression tree, you can interprets, averagely, but random forest becomes complicated because it is an aggregation of different trees. Then for feature interaction, right? Regression, feature interaction, you can do it manually, and regression tree is automatic, and random forest is automatic also. Then overfitting risk, for overfitting for linear regression is low. Under regularization, it is high for regression tree, and it is also low for random forest. So if overfitting is a concern, random forest is most likely going to give you a better result than regression tree and linear regression. And talking about performance on nonlinear data, linear regression is poor on nonlinear data. Of course, it's called linear regression. So if you have nonlinear data, it's going to do a bad job. Regression tree is moderate and random forest is strong. So across this criteria, it looks like random forest seems to have some advantages over linear regression and regression tree. Now, 17.2, let's talk about data set. We are talking about California housing. I think we've used this a couple of times in previous videos. So the description of the data set is such that the California housing data set contains housing information for districts in California, with features such as median income, house age, average rooms, latitude and longitude. And the target variable here is median house value in each district in hundreds of thousands. So that means I want to predict median housing value based on these targets, the median income, house age, average rooms, and latitude and longitude. Talking about the location. The code implementation in this case. Now let's set up the whole thing and process data. Of course, NumPy, Pandas, Matplotlib for visualization, NumPy for numerical work, Pandas for data analysis, and you have scikit-learn. Every other thing here is for scikit-learn. That's sklearn, which is the most popular thing for machine learning. So, and of course, the California dataset, this is how you bring it out from scikit-learn. The dataset, you import fetch California housing. So we give it a name here. So I think it's better we have, as usual, you want to show the line numbers for easy referencing. Okay, so load the data set in line 12. So data is fetch California housing. So from that, you can extract the features. So you have x equals pd.data frame, data.data, columns data.feature names. And so this way you can actually easily visualize what that looks like. And then here you have y is pd series data the target, then median house value. That's what you actually predict. And of course, we can visualize X and Y the way this is right now. Okay. So then you can do X train, X test, and all that to split into training and test sets. We've done this a couple of times. So it's definitely not new. So we can run this and it takes a bit of time. So that status is on. Now it's done. So I want to create some space under just to visualize the X and Y. So for this, so if you have X here now, this is what it looks like. All right. And then if you also want to see Y, this is also what that looks like, you know. Control enter. Okay, that's median house value. That's what we have named it here. Uh, you know, based on what we have right here. Now, of course, we have done the whole split into training and test. We are using 20% for test side, so 80% for training. Now, for the model training itself, now we are talking about three things: linear regression, decision tree, and random forests. So now all of this we have already imported from here. So from sklearn.tree, we have decision tree regressor. From sklearn.ensemble, we have random forest regressor. From sklearn.linear model, we have linear regression. So remember when we were doing classification, it was I think it was decision tree classifier, random forest classifier, and all that, right? But here we're talking about regression, so it's regressor, not classifier. So we initialize the model. So we say models for linear regression, that's linear regression like this. So we have something like a dictionary of models. So linear regression, decision tree regressor, and random state for the two to ensure that the values don't change. Random forest is random forest regressor. Now this one requires estimators because we are aggregating trees. So it's more like we are putting like 100 trees together to get the result here. And that is to make sure that we don't have overfitting. And random state is for the two to ensure there's no change to. So you can now train and predict. So for predictions, we have for name. So for name, so name is an initial is an indexer. That's what I like to call that. I think until I get a better name for it. So it is way of indexing. So model. So these are the models now. So it's more like you want to iterate over these models. So for name and model in models dot items, each item here, they have model fit x string. So it's more like you're iterating over these three models to fit them, on the trained set and the trained sets x, both x and y. And then for predictions now, you put the name, whatever the name of the model is, like linear regression, decision tree, and all that. You put it in and have model predict x test, right? So we click enter. That takes a bit of time, and the star is on. So it's iterating over the three models to fit them. That's why it's taking a bit more time than what it would take for a single model like we have been used to. So it's still running, taking some time. Yeah, now it's done. So it takes a bit more time than what we have been used to in previous situations when we're training just single models or something. So now it's settled. Then we go for evaluation. Now that you have fit the model, you have also trained and predicted, and the next thing you want to do is to evaluate the model to see its performance. So here we're using a Python function. We define a Python function called evaluate models, which takes the true value of y, and then the predictions, the predictions that are coming from here, right? And we have the true value of y. Whatever the true value of y is, that's the observed value, so to speak. And then this is line 3 is initializing the results. So this is an initialization for the results. So you now say for name, y period, that's predicted value in predictions dot items. Then you want to find the mean square error, you want to find the R2 score, and then you now append the results. So you say results append the name of the model, the mean squared error, and the R squared score, right? Those are the metrics for evaluating, and then you return them as data frame in terms of results and the columns model MSE and R square value. So evaluate all. So you now have results df, evaluate models, y test predictions, result df. So it gives us that as a data frame. So for linear regression, the mean squared error is 0.5 to two decimal place, that's 0.56. The R squared is 0.57. For decision tree, it's 0.50. For random forest, is 0.26. Like we learned in previous videos, right? For mean squared error, the lower the better. For R squared, the higher the better. So you can see that like some kind of inverse behavior between MSE and R squared. So linear regression has the highest MSE, followed by decision tree, followed by random forest. So it means that random forest is the best of the three models going by MSE. Now, when we come to R squared, the smallest is 0.57 for linear regression, 0.62 or 0.58 for linear regression, 0.62 for decision tree, and 0.81 for random forest. So going by mean squared error and R squared, random forest takes the cake. It's the best across these two metrics. So sometimes you can have some models that are really confusing, like you cannot establish a clear pattern, so you may need to adopt maybe one or two other metrics to actually, or in fact you have to even go as far as cross validation to make a decisive decision on which of the model is actually better. But in this case, it's clear that random forest works better. Okay, so talking about visualization now, so you compare actual versus predicted values visually. So we want to compare the actual value, that's the observed values from the data set, and then what we get from the predictions we get from the linear regression, decision tree, and random forest, like that. So and then we do the label linear tree and forest, and that's just a pictorial thing in this situation. So you have the sample index. All right, so the housing value in hundreds of thousands, right? So you see the blue lines are the actuals, while the orange is linear, and tree is green, and forest. So you can see that the forest is matches more closely to the blue lines than other ones, and of course that as confirmed by the result of by the metrics we have when we evaluate the model. So the key insights and summary here involve the following: observation, random forest had the best performance, of course, for across all metrics due to ensembling and reduced overfitting. Of course, that's to be expected. Decision tree outperformed linear regression because it handled non-linearities and feature interactions better. Linear regression was fastest and simplest, but made strong linear assumptions. So linear regression is faster to compute, but you're not guaranteed of high results. So there's always a trade-off between interpretability, how easily you can interpret the result, versus the accuracy. So you see, random forests are less interpretable but more accurate. So you want to have that trade-off as much as possible. In conclusion, regression trees are useful for capturing nonlinear dependencies, but are sensitive to overfitting, while random forests regeneralize better by averaging multiple trees and significantly improve accuracy. Linear regression, while simple and interpretable, struggles with complex data because it's only suitable for linear relationships, right? Choosing the right model depends on data complexity, interpretability needs, and performance goals. So if you have a simple data that has linear behavior, so you can just settle for linear regression. Using random regression trees or random forests can lead to the data overfitting, right? Because the data is too good. I mean, the model is too good for the data, right? So you want to be sure of what exactly your goals are and go by that. So with this, we come to the end of this video. Let me know how helpful this is for you, and if there's something you'd like me to do, like to try out and all that, feel very free to let me know. If you have subscribed to the channel, thank you so much for that. If you haven't, please go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. And be sure to join as a member if you can. Feel free to join as a member if you want special privileges like having a badge displayed by your side, or you can even go higher. And some videos will just be made for members, or members get to see some videos before other people see it. And then you can even have my PDF notes of my maths playlists, and of course, based on request, by the way. And of course, you can also have consultations with me, depending on the group of membership you join. So currently, I have bronze, silver, and gold access. You're free to join as a member as you like. But of course, if all you do is subscribe, you're good to go. You still get the benefits you've been getting for sure. So till I come your way again, keep doing data right. Be sure to like and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing data right. Bye.